Hey, in this video I will show you how you can implement hash tables from scratch in C, but also just to learn how they work. So maybe you don't know by the name of hash tables, but you've probably used them already. So in other languages like Python, they're called dictionaries. In C++, they're called unordered map. In JavaScript, I think they are just objects, and so on and so on. So it's a way to map a key to a value, basically. And so how they work is a hash table is just a big array, and the indices of that array are the hash of the keys. So the user is gonna give you a key and a value. You're gonna pass your key through a hash function, and the hash function is gonna return you the index inside of the hash inside of the array that is contained in the hash table. And what a hash function is, if you don't know, is it's used in multiple domains like cryptography and so on. Maybe that's where you've heard it from. Yeah, it's just a function that takes any input, like any number of bytes, let's say, and returns just some integer, like most of the time at least. And so, for example, I don't know, you give it the string foo, like 3 characters, and it will return the number, like for example 32. And you give it another string, and it will give another random number. And there is a lot of context around hash function, how to make them safe, how to make them the most random as possible, because we want them as random as possible to make the hash table effective, for example. Or in cryptography for security, we want them as random as possible. There is a lot to dive into, but like for this video, let's just assume that it's just a function that takes some bytes and that returns an int or an index. And so yeah, there is multiple ways of implementing it. You can see actually in this representation, maybe on Wikipedia, where it's a bit clearer. So you have John Smith is, for example, the key, and then it's going to be passed through the hash function. And then the hash function is gonna return the index 2, and that's where we're gonna actually store the value that is associated with John Smith. And you can see that Lisa Smith has through the hash function is the value of 1, and so on and so on. So each string key is mapped to an index, and then at this index we store the value associated with that key. And there is multiple ways of implementing those. Because one of the big problem is that hash functions can have collisions. So for example, like if you have the string John Smith, that in this case returns 2, maybe later some other random string like foo, maybe the hash function returns also the index 2 for that one. And so here you have like 2 keys that map to the exact same index in the array. And then what do? You need to find some efficient scheme to deal with hash collisions, and that's where most of the implementation differences come into play. So here they talk collision resolution. So yeah. And for example, one of the simplest method is separate chaining, which we won't discuss in this video. Today I chose to implement the open addressing one, which is one of the simplest one of to solve conflict, with linear probing, again, just the simplest one. It sounds like fancy names, but it's really simple. So this is how it works. So for example, here Lisa Smith has just his index, her index is clean, so no conflict. But here you see that we insert John Smith at index 152. And then we insert later Sandra D, which has also coincidentally the same index, so 152, as John Smith. And the thing we're going to do is that, so John Smith already occupies that space. And so to solve the conflict, we're just going to say, okay, the result of hashing this this key is 152, but since there is already someone there, we're just going to increment it by 1 and put it in the next spot. So and next time we want to search for Sandra D in the hash function, in the hash table, we're gonna hash it, and then look it up at this index and see that it's not the correct key. And so we're just gonna iterate and go to the next one until we found Sandra D. And here you can see that Ted Baker already gets hashed to like 153, which unfortunately is occupied by Sandra D. And so we're also gonna increment it by 1 and put Ted Baker just below it. I think that this will become clearer when I show the implementation. So yeah, that's the theory. Now on to the example. I've already implemented that on stream yesterday. So just simple main function. Let me copy my stuff. Yep. So this is the main structure for hash table. As you can see, it's relatively simple. We define the bucket count, and bucket count is just the length of the array. Those are called buckets, and each of those is one bucket. So yeah, we have a bucket, a struct bucket, which has a key, a value, and a tombstone. Don't worry about the tombstone yet, it will come into play later. But just, a key value pair. And then the hash table itself is just a bunch of buckets, and it's just an array of buckets. And here I define the fixed sized array. That was my notes. So I defined a fixed size array of buckets. But yeah, of course, if you want a more fancy implementation, you have an array that can be dynamically resized when you run out of space for new keys and so on. Next, let's copy paste quickly the new and destroy function. So as you can see, it's relatively simple. I just malloc a new hash table. I set all its elements to 0, which is important to indicate that this thing is empty. So the way I check if it's empty is if the key is null, I say it's empty, basically. And destroy, you can probably guess, we free the keys, since in this case I've made it simple by not making it generic, and so the keys are just strings and the values are just integers. And so we just free the key, free the hash table itself, and that's it. Let's actually make one hash table. ht is equal to hash table new, and let's delete it afterward. Destroy ht, like so. And as you can see, no output for now, but it will come into play later. Next, maybe a small function to print the hash table. So yeah, this does what it says, just printing the hash table, print ht. And here I've given the size of my hash table to be 8. Of course, that's a ridiculously low number. In real life, you would want a much larger table most of the time. But this is just to keep the output simple. And so you can see here that it prints every bucket in the hash table, so every entry in the array. And for now, all of those are just empty. Next, I'm gonna copy my very simple and dumb hash function that I did. So here is the hashing function. So as I said, it takes a string or any kind of bytes, but in my case, a string, and it returns an index. So just an int 64 in my case. And so there is a lot more fancier ways of making a hash function. By doing random bit shifts and so on and so on. But in my case, I wanted to keep it simple, so I start with a digest. The digest is a common name for the result of the hash function. So the digest starts at 1, and then I just iterate over every single byte of my string and multiply the digest by the value of that byte and modulo make sure that it doesn't go over the bucket count that I have. And this is my very dumb and simple hash function for this example. Next, I'm gonna have this a bit slightly more involved function, which is called get bucket. So what this will do, it's we're gonna give it the hash table, we're gonna give it some key, and it's gonna return the bucket that we found for that key. And so what it mainly does is like it takes the key, gets the hash of it, and then get the bucket that is located at that hash. And there is a for loop for the probing I was talking about. So if this is like empty or so on, we're gonna go over the next iteration and go to the next possible spot for that key and check like if it's the same key. Well, then we have found the bucket. Otherwise, we're gonna return the empty bucket that we find. So yeah, that's mainly like so. If we found the key, if we found the bucket for the key, it will return that bucket. Otherwise, it will return an empty bucket. And this is used later for the command method. So, for example, one of those is hash table insert. Of course, if you want to insert an element in the hash table, so first we use get bucket. And again, don't worry about this false and like this skip tombstone argument. I will explain it later. For now, we can just assume that this doesn't exist. So we get the bucket for this key, or we try at least. And if this spot is empty, we duplicate the key. So yeah, that means it doesn't already exist in the table. And then we just set the key to this potentially empty bucket to the key, and we set the value to the value, and that's it. And if it already exists, we skip the strdup since we don't have to waste time deallocating and reallocating the thing. But basically, we update or create the value at that spot. And let me show you that it works. So hash table insert. For example, we want to insert the key foo of value 42. Up. And here you can see that it picked the index 6 to store the key foo with a value of 42. And you can do that for a bunch of keys, of course. You can say bar, you can say baz, and all the time, every time change the value. And so you can see here I have a very garbage hash function, so it stored them next to each other. I think if maybe I do like a different key, like const, why not? You can see it picked the first spot in the buckets in the array to store const, and the other one at like other indices. And you can see it's kind of random where it puts them. And yeah, that's how they are stored. Next, let's implement the delete function. So again, very simple. We get the bucket, very similar to insert, and then we just freeze the key and then set everything to 0 and mark it as a tombstone. This will come into play later. Don't worry about it too much for now. But so again, this works if I maybe do... So I print it after I insert all the elements and then I delete. Let's say I delete, I don't know, who, why not? Well, I should maybe just put a delimiter between the two, otherwise it's a bit confusing. So you can see that's when I insert everything and then I delete foo, and you can see that, yeah, the cell where the bucket where foo was stored is deleted and marked as a tombstone. That's what the little t means. Next, we just have two very basic functions as well. Just hash table get, which will just return the value associated with a key. And if that key does not exist, it will crash the program. And I have another function which is hash table contains, which you can probably guess it's gonna return true if the key is included in the hash table. So let's do some demonstration for those. Let's do printf d of hash table get. Let's say we want to get I don't know, bar. Yeah, I haven't deleted that one. Up. And we can see that bar, which is 41 here, is 41 here as well. And of course, contains, you can probably guess as well, like that for bar it will return 1, which is true, and if I say just some random key that does not exist, it will return false. And the way those are implemented is, again, very simple. It's just a get bucket and a check if it's null or not. And yeah, in those cases, you can probably just read it. So yeah, that's the main implementation. I think with that you already get a pretty good understanding of what hash tables are. Next, but then there is like some issue with the deleting, because that's where the tombstone thing comes into play. So you can see that if we have conflicts like so, then we have some kind of like chain that goes on, like you store John Smith, then you store Sandra D, and then you store Ted Baker, and like they are like since there is conflict, they are a bit mixed around or like shifted around. And let's say in the future I just delete Sandra D, so I would delete Sandra D, and so this would be null. And then, but Ted Baker still exists. And then after I delete Sandra D, I will try to get Ted Baker. And what the algorithm will do for now is it will say Ted Baker, okay, I hash it, okay, it's 153, and then it sees null. And so he's like, okay, but then Ted Baker doesn't exist. But it does exist, it's just that it was shifted because of a previous conflict. And so that's why you need I mean, there is multiple ways of handling this, but one of the simplest is having some kind of flag for the bucket to say if it's a tombstone or not. And basically what you're going to do is when you delete an entry, you're going to mark it as a tombstone. You're going to make the pointer equal to null to mark that it's empty, but you're also going to mark it as a tombstone to indicate that there was a potential conflict, and that when looking for a key, you need to like consider the tombstones as not empty. So that's what I do here. When I delete it, I mark the bucket as a tombstone, so tombstone is equal to true. And when I insert it, I toggle that flag back, so tombstone is equal to false. And it comes into play here in get bucket, where if the bucket is empty, but marked as a tombstone, it's okay in some case. So if you provide the argument skip tombstone to true, it's gonna make it so that it's okay, it will ignore the tombstone. It won't consider the tombstone as empty. But if this flag is so if skip tombstone is set to false, it will consider the tombstone as empty. And so this comes into play when we can see when in delete, get, and contains, here we always want to set skip tombstone to true, because we want to get the actual key ignoring the tombstones. But the only case where this changes is in insert, where if there is we say skip tombstones to false, because if we encounter a tombstone, we actually want to fill it with the new value. And so yeah, that's why tombstones are present. And I guess a good way of demonstrating this would maybe be to actually show it instead of explaining it. So let's just fill the whole thing. 2, 3, 4, 5, 6, 6 and 7. So that should fill the whole thing. No need to print it, I think, but let's see. So yeah, here I have filled 1, 2, 3. Ah, yeah, I need an 8 one. Okay, so this is a completely filled hash table. And now let's say I want to delete foo4 for some reason. That's fine, it's marked as a tombstone. And then later I want to get, I don't know, foo7. Here you can see it works, but if I remove the hash table, the tombstone kind of thing, so if I remove the tombstone flagging, okay, it won't work in this case because maybe it's different, but let's say, okay, I actually have to find someone that will make it crash. Oh, that's, yeah, okay. So of course I had to like find the conflict manually, but so you can see that foo4, oh fuck, foo4 is the one I deleted. Maybe there wasn't a conflict at this place. Okay, finally, I found a conflict. So here you can see I fill the whole hash table. Then I make a delete, but without the tombstone implementation. And then when I try to query a key that actually does exist, so foo6, it will crash the program and say it the hash table doesn't contain it. But then if you go back to and set the tombstone flag to true, then it works, because it has understood that this empty cell is actually marked as a tombstone. I should maybe my camera is hiding it. So this empty cell is actually marked as a tombstone, and see, so when you try to get foo6, it knows that it needs to skip that one. Anyway, that was a bit complex, but yeah, that's basically how you handle how you could handle deletion in a hash table like this. And yeah, it's not the most optimized way, because at some point the tombstones are filling your hash table and you need to like recreate it in a way. But yeah, it's like the simplest way of handling it. Anyway, that was the basics of hash tables. I think it was a bit of a long video, more complex than the dynamic array, but it is a more complex data structure. Let me know if you want me to do some extra videos on like the optimization you can do on hash tables. Like there is open addressing, there is multiple ways of doing that. So for example, there is a quadratic probing, or there is double hashing, and quadratic probing is actually what is used in Rust apparently. And there is like better ways of handling the tombstone thing by not having tombstones. I could also just show you the separate chaining, which is less optimized, but a more intuitive way of kind of more intuitive. Yeah, just let me know if you're curious about those things. I did explore them on stream, which I will link in the description, but yeah, anyway. It's a really nice topic, and yeah, hope you enjoyed this introduction, and yeah, see you in the next one.